Okay, so the first thing is the del operator, just like a refresher about this new like notation thing. Like, what is this triangle thing? So I'm going to call it the del operator. And what it means is that you're taking the derivative of each component or the partial of each component. And so from that, we have three definitions that come out. We have the gradient, which we know, curl, which is something new we are learning this week, and the divergence. The divergence is you add each of the partials. For the curl, you might see this like complicated formula and be like, how do you memorize it? Well, you don't have to memorize it. All you have to remember is this matrix. So you can write the ijk as a column, write the partials as a column, and given some vector field, write each of the components. And you'll see that if you take this determinant, you get exactly our three components of the curl. And make sure you keep it in the correct order. Like, don't have this third term as the first component. That would be incorrect. So make sure you keep it in the correct order. This term, then this, then this. Okay, and so what happens, this our function f. If our function f is in 3 dimensions, so it has an m, an n, and a p. What happens if we get rid of the third dimension? We get rid of the z variable. Then we have scalar functions in 2 dimensions. So there's an x and y. What happens when we're in 2 dimensions? Well, the gradient, there's no z term. So this term becomes 0 if it were in 2 dimensions. Then what happens when we're in 2 dimensions for curl is that this term ends up becoming 0, and this term also ends up becoming 0. And the reason for that is because if you have a function with just an x and a y, so here I've written in green, we can do the determinant, as I said, for how to find the definition of the curl. When you do the determinant, you would do like your I component gives you this partial with respect to y, which is 0, minus this partial with respect to z, which is also 0 because remember there's no z's. So when you take the partial of z, there's nothing to take. So this whole term becomes 0. And you can do the same thing with the j component. You get 0, so you're only left with the k component. And what happens to the divergence? Well, there's still an x partial, there's still a y partial, but there's no z variable. So this becomes 0. So in 2 dimensions, if we just have an x and a y, these are our formulas. Here. Okay. Any questions on those definitions? Okay, and then we have some special notes. So these are some special properties that we know, which is that if gives you 0, and the divergence of the curl will also always give you 0. So those are 2 properties. And so from that, we know that if the curl of the gradient equals 0, then if f is your gradient, so take this capital F, and we're saying that our gradient of lowercase f gives us some vector capital F. This tells us that the curl of our capital F will be 0. So if we have a gradient, then the curl is 0. Then the next question you might ask is the converse true? Like, if the curl of f is 0, does that mean this function is a gradient? Does anyone have any? If you think it's true, raise your hand. If you think it's false, raise your hand. False. Okay, let's observe a little bit and see what these mean. Okay, so let's see. The problem is this true? Do we get if and only if? Like, is the converse true? Let's look at what curl of f equals 0 means. If curl of f equals 0, that means that each of these components has to be 0. So like for this first term, if the partial of p over y minus the partial of n over z, if that equals 0, then when we add this term on the other side, we get that the partial of p with respect to y equals partial of n with respect to z. So we get this first equality. If our second term equals 0, then we get this next equality. And if the third term equals 0, we get this equality. Now, what does it mean for f to be a gradient? So this means your function like m and p is a field. Now this should look a little bit familiar. Does this look familiar for anyone? It's the component test, right? When we were checking if something is a gradient, we checked, are all of these equalities equal? If they were equal, we saw that it is a gradient field. So this, if and only if, is true because it's the component test. It's exactly what the component test says. Any questions on that? Yes.
So if the curl is 0, it's a gradient.
Mm-hmm.
And if you take the gradient, so the curl is 0, and then does that apply to divergence?
So if so this second one is saying like, oh, let's not. If f is your curl, then divergence of f equals 0, then yeah, you could say that, then that must be a curl, but we don't really have a definition of what it means for something to be a curl.
Yeah.
So I guess this like backward direction isn't like a theorem.
Okay.
Yeah. This theorem is like a defined theorem, and it's known as the Poincare lemma. So this is definitely true. Okay, so that was some definitions. And so from this point on, what we're going to be dealing with is curves that are simple closed plane curves. And that's how we're going to start using like Green's theorem and like all the other theorems. And what a simple closed plane curve means is that first simple, so it doesn't cross itself, meaning like it can't be, your curve can't be like infinity because it can't cross itself here. Closed means that it should start and end at the same point, so it's like a loop. And a plane curve just means that it lies in one plane, so you can't have like a curve going from this plane to some other random plane. Okay, and this brings us to a few graphs first. So let's explore vector graphs. So if we do curl of f dot k, what is k? K is 0, 0, 1. Just like how I component is like 1, 0, 0.
One question. Isn't the curl of the cross product between the gradient and the vector?
Sorry, what?
The curl, isn't it like the cross product between the gradient and the vector?
The cross product between the gradient. Kind of. Like curl is, yeah, gradient and cross product. Vector field. And so when we do the gradient cross the vector field, we get this whole thing. That's the definition. And so if we take this curl, so 3 components, and we dot it with k, then we get 0 times this, plus 0 times this, plus 1 times this. So the kth component of our curl is just this last term, partial n over x minus partial m over y. And for in 2 dimensions divergence, we said there was no this term, so the divergence is just this plus this. So right now we're focusing on 2 dimensions, like a 2-dimensional vector field. So let's do an example. So this one we saw f is defined as cx, cy. It's an expansion outwards. If you were to compute the curl, you end up getting 0. And if you compute the divergence, you get 2c. Okay, and let me do another example and then see if you guys notice a pattern about what is curl saying and what is divergence saying. Okay, so let me do another. Saw this last week. This is the counterclockwise rotation vector field. If we compute the curl, we see that we get a number, 2c. But the divergence, if we compute it, we get 0. So does anyone notice anything, like, see how it's opposite? Above here, we got curl 0, divergence something. Here we got curl something, divergence 0. Yes.
The first picture is just like showing the expansion. There's no like spin to it.
Mhm.
And the second picture is always showing spin and then no expansion.
Yes, exactly. So that implies that curl is telling you the rotation at some point, like infinitesimally. So there's no rotation in this first picture, so the curl is 0. Expansion. So divergence is some positive number. If divergence was a negative number, it'd be compression.
What are you classifying as M and then?
M is always your first component, N is your second component in your vector field. So like F is given as MN in 2 dimensions, which is right now CX, CY. In 3 dimensions, I define it as M and P. Okay. And so in the second picture, there's no expansion at all or compression, so divergence is 0. But there is a lot of rotation, so the curl is 2c. Okay, what about a third example? So this is showing us shearing flow. So like above the x-axis, your vectors are going one way. Below the x-axis, your vectors are going another way. And if we compute the curl, we end up getting -1, and the divergence is 0. So that means that why is curl -1? So the reason is because our vector field, if we start at like the top right, we go this way and then our vectors start turning that way. So this is going clockwise. So clockwise curl means you should have a negative value. If curl was positive, curl is always defined as counterclockwise. So if our vector field was, our vectors were going this way at the top and then to the right at the bottom, then this would have a positive curl. Positive curl. But right now our vectors are going clockwise, so we have a negative curl. And there's no divergence, there's no expanding or contracting or anything, so divergence is 0. Yes?
Like, what are the key differences between circulation and curl?
Circulation.
Circulation is like the work done in the field. So is it
Mhm.
related to curl, or are they just kind of like different actual amount, like sharpness of it? Like,
I believe they're, so curl, you can think of, so curl is this formula, right? We have our 3 terms in 3. This first term is telling you what is the circulation Z plane. This circulation in the ZX plane. This term is telling you what is the circulation in the XY plane. So like if you have some curl, like say a curl was a number, like you have some vector field, you computed the curl, you got a, remember that output of curl, you got that in the YZ plane, you have no rotation because curl is rotation. But then it tells you that then the second component being negative tells you that you have a clockwise spin in the ZX plane, And the positive 1 tells you that you have a counterclockwise spin in the xy plane. So like how you get curl is you're looking at this, like you take the circulation in each of the is how you get curl.
But if circulation is like 4, then like, is circulation telling you how, is it telling you how much you're spinning, or is it just like, or like what is it? Is it saying like how, is it kind of show you like the shape, like how tight it is, or?
Not like, let me see. So like circulation, well, circulation is like telling you, it's still telling you like a little bit about rotation. It's like how much spin is your vector field going to generate in this specific plane. So like circulation is telling you how much spin is going to happen in the YZ plane, and that tells me the first component of our curl.
Okay, and you were just saying like that would be, so that would be 0, and then clockwise and counterclockwise.
Yes, clockwise is negative, clockwise is counterclockwise is positive. Okay, any other questions about this, these examples? Okay, so then let's move on to a quick refresher. Okay, so remember from last week that we have the definitions of circulation and flux. So these were our definitions from last week. And so say we had this question here. So it says, compute the counterclockwise circulation in the plane of this vector field along the region determined by this highlighted region, which I drew out. So x should be greater than or equal to y squared. So we see it's above the orange or the green, wait, x is, it's below the orange line, and y should be greater than or equal to x squared, so it's above the green line. Okay, and now, so think about what parameterize, using last week's material, so using these previous definitions, think about what parameterization you want to use for our green line and our orange line, and see if you can get any results. So take like 2 or 3 minutes to think about this question using what we know from last week. So does anyone have suggestions for how should I parameterize my green curve? So I'm gonna call it gamma 1 of t. Yes. Yes, that's the greatest one to pick. And then what about for my orange one? Yes.
You do t squared t.
Yes. That's also a very clever choice.
You do would a t with root t.
That also works, yeah. Yep, but to make things easier so we don't have like square roots, this is also a nice choice, t squared t. So
It's a parameterized necessarily.
using the methods we learned from last week, we have to parameterize it because our definitions are that we're gonna plug in our parameterizations into our function and then multiply by the derivatives of those parameterizations. So we should parameterize here. Okay, so knowing these parameterizations, we can now compute. So we're computing the circulation of this whole path. But in order to compute the circulation here using last week's methods, we have to split it up into two integrals. This is because we need to compute the circulation along the green path first, plus the circulation along the orange path. So if we first compute the circulation along the green path, well, let's also compute the derivatives while we're at it, so we can just plug stuff in. So the derivative of this is 1, 2t. Oh, also a very important note is what is your t going from? In our first parameterization for t squared, we go from 0 to 1. That's fine. So t goes from 0 to 1. But for our orange parameterization, notice we go counterclockwise. So if we want to use this parameterization, t squared t, we should be going from 1 to 0. And you can always check that you're going in the correct t direction, because you can first plug in, what point do you get at t equals 1? You get 1, 1. At the end point, what happens when you plug in t equals 0? You get 0, 0. So this is the correct parameterization. Yes.
So if you were writing that with like inequality, would you still, like, how would you write t?
You can write, so I guess you could, it doesn't really make sense with inequalities, which is why I didn't write it as an inequality. But you don't really need to write it as an inequality. The only reason I'm writing it is because that way we know in our integral what's going to be the lower bound and what's going to be the upper bound. Yeah. Yes.
So why do you not take the derivative?
We haven't did it yet.
Oh,
So let me do it. Yep. So second derivative is going to be 2t and 1. Okay, so plugging in our green. So we're going from t from 0 to 1. Our m is negative 2y. And so what was our parameterization for y? We said y is t squared. And so we're going to have negative 2y, or t squared, times what is the derivative of x with respect to x? Or yeah, x with respect to t, that's 1. Plus our next term is 5x. So we have a 5. And what did we define as x? We define it as t. What's the derivative of y with respect to t? That is 2t, which we found here. And dt. And you can calculate that integral since now we're all in terms of t, and you get 8 thirds. Yes.
This whole example was like last week.
Yes, last week.
You didn't use anything.
Nope, nothing. Okay, and now we need to take the integral of our orange path over our orange path. So we do the same thing. Now our t is going from 1 to 0. So I put 1 on the bottom, then 0 on the top. Our function is negative 2y. So we have negative 2. We define y as t. And then the derivative of x with respect to t is 2t here. So 2t. Our next term is 5x. So plus 5, what is x? We said x is t squared. the derivative of our y parameterization with respect to t is 1 dt. And so in order to evaluate this integral, you could just straight evaluate it where your bounds are from 1 to 0. Or if you're uncomfortable with that, you can flip your bounds, but make sure you bring out this negative sign. And you get negative 1/3. So yeah,
You could also do it without parameterizing this.
yes, that using Green's theorem.
Exactly.
Yes,
And
so
it's a bit easier, right?
yeah, so that's the point of this example. So yeah, so this is the first version, which we learned last week. And we see that it's a lot of work, right? We computed the integral over the green path, which is 8/3, plus the integral of the orange path, negative 1/3. And we get 7/3. Or as Alberto said, we could use Green's theorem. Okay, any questions before I move on to Green's theorem though? So this was all last week's stuff, or like the long way. Okay, so what does Green's theorem say? Green's theorem says if we have some simple closed plane curve as our curve, then the counterclockwise circulation of f is going to be defined as the double integral of this dx dy. And notice that this term is exactly our kth term of the curl. And equivalently, so Green's theorem also has like the flex version, which we see that it ends up being this. The integral of this term, dx dy.
So one question,
Mhm.
over there with the circulation equals the curl of that dotted with K.
Mhm.
K is a vector 0, 0, 1.
Yes.
But is it that by like definition, like all K's is 0, 0, 1, or just in that case?
K is always 0, 0, 1. As long as you're referring to like the K vector.
Oh,
So, the reason it's like that is because circulation, we learned it in 2D, so you're simplifying curls into.
Yep, because circulation is in 2D. See how like each component was, I said only like YZ plane or ZX plane. So circulation is always 2D. And so we can take the curl, but take the 2D version, and we end up just getting this.
And so circulation and flux are the derivatives of curl and divergence respectively, kind of, with the Green theorem.
Yeah, kind of. Notice that for Green's theorem though, technically, Green's theorem is only one version, just this circulation version. The reason is because I can get this formula, my flux formula, by using what's in the green box. So they're technically the same definition, just in a different perspective. So why is that? Let's look at the flux definition. So flux says that we're doing the integral of partial m over x plus partial n over y. So flux is, oh wait, actually flux, let's start with what flux is. It's m dy minus n dx. Let's rewrite it so that the n is in the front, or like the dx part is in the front, plus m dy. Now, what does Green's theorem say? Green's theorem says that we should do the double integral of n over x minus m over y. So knowing this flux, we're trying to find this circulation integral. We apply Green's theorem for the circulation. And what did it say? It says we do the double integral of the second term with respect to x. So our second term is m, and we take that with respect to x. So m with respect to x minus our first term. Our first term right now is negative n with respect to y, dx dy. So we get the double integral of partial m over x. If we don't want this negative here, we can take it out, and we get plus partial m with respect to y. And this is exactly our flux version of the definition. So we see how we used Green's theorem, the circulation version, to get our flux definition.
So it says counterclockwise circulation, on the formula up there or whatever.
Uh-huh.
So I noticed that like basically when it tells you that it's counterclockwise, if you do it that way, and if it's clockwise, you put a negative in front.
Yep.
But for outward flux,
Mhm.
I don't understand, like, is there a question that'll be like, some indicating that you took the negative outside if it's like inward, or do you just calculate the flux and the value that you get is gonna indicate whether it's inward or outward?
So flux assumes that, like, say you have this circle as your curve. Flux is, to get the definition of flux, it's in like the outward normal as your positive flux direction.
Right, but when you're like, there was a practice problem that you had to put a negative in front because it
was
indicated it was clockwise. But would there ever be a question that somehow indicates to you that you put negative in front of the flux because
It was like in,
like it's not going to tell you it's inward, right? Like isn't the
it would tell you what direction is the normal vector. Like, is the unit normal, like, assuming unit normal is outwards.
and then okay, so assuming if it's like assuming unit normal is inward, then you put a negative in front. Or would, because I'm confused, like if you get a negative value, is that
Yeah, I think for inward, like if it was the opposite way, then yes, put a negative sign. I'm not sure if I've encountered that yet. Usually most of them are like outward normal.
okay? But then, so my question is also like for the circulation part,
Mhm.
where there was a question on the practice problems that you actually negative in front because it was like clockwise.
Yes.
What can't you also just get a negative answer when you're calculating the circulation rate?
Yeah, you can.
Right. So then, what does that indicate?
That means that it's moving clockwise.
Okay, but if the problem tells you to move clockwise and you're putting a negative in front, aren't you indicating whatever it is indicating? So if you're going to calculate something that's clockwise, then you put a negative in front because the right answer is making it counterclockwise.
Let me.
Because I just feel from the practice problem, I got a positive answer and then I checked it, got it wrong. I was like, oh, it's just clockwise.
Was it number 30?
Yeah, probably.
It was written incorrectly. There's a typo. So yeah, and Cooper just changed it, so it should be fixed on the practice
Okay, I'll
problems.
check.
It was like it was moving counterclockwise, and you got a negative number. Like it said counterclockwise. You computed it, and you got a negative number. But it should actually be a. Oh yeah, wait. And it was a negative number.
Okay. The problem I'm talking about, it said clockwise and you got a positive number, and then I had to put a negative on it and I got it right.
Clockwise. Because if you got a positive number, whatever you get through circulation is its counterclockwise spin. But because it's clockwise, you have to negate it and put a negative number on it. So like, regardless of negative, positive, whatever, clockwise just reverses your answer. You
Right.
get the negative version of it. It's not saying like if it's positive, like don't associate like negative with, okay, you kind of do, but yeah, I see what you're, okay. Just ask on the answer. Give that to
Okay.
it. Yeah, I see your, I get the confusion. Okay, so let's get back to this. So next thing is, when can we use Green's theorem, right? So first, it has to be a simple closed planar curve, which I mentioned. So you can't have the curves crossing. It should be closed. So start and end point should be the same. And it should be planar, so on the same plane. Also, it should be a simply connected domain. So a simply connected domain means that it should be connected. So like you could draw a line around it. And also there should be no holes.
I just scroll a bit up.
Yeah.
Just like a thing.
So think about this first graph or this first picture. Yep. So the donut. And my question is going to be, is this a simply connected domain? So if you think the answer is no, raise your hand. Okay, great. Consensus is no, because there's a hole. What about the second one? If you think it's no, raise your hand. If you think it's yes, raise your hand. Yep, great. Because connected, control, and no holes. What about the third one? If you think it's no, raise your hand. And yes, raise your hand. Okay, great. And the reason is, even though it looks like there's like blank spaces, if you imagine kind of like lassoing the three pieces together, then you get this I shape, and that is connected and there's no holes. So it is a simply connected domain.
But it's not connected, right? In the middle.
So it's not like you see there's gaps, but the idea for this one is that if you kind of combine these three things together,
Oh,
you get the I. And that is, so it's like connected simply, like if you can connect it,
okay.
then it's connected and no holes. And what about the last one? If you think it's no, raise your hand. Right, because there's a hole in the middle, like this highlighted part. Okay, any questions on that exercise? Okay, so now going back to our last example. So the last example we did using last week's material, where you saw it was a lot of work, right? The long way. We had to compute the integral over the green path, then plus the integral over the orange path. Instead, we can use Green's theorem because this is a simply connected domain. It's connected, there's no holes. Our end and start point are the same. So what does Green's theorem say? Green's theorem says that this integral is going to be double integral of this kth component of the curl, dA. So now we need to see what is m and n. So m is the term that is associated with I hat, or your first component. N is going to be this second component. So we have m equals -2y, n equals 5x. What do we need? We're going to need the partial of m with respect to y, which is -2. And we're going to also need the partial of n with respect to x, which is 5. So we get this double integral of 5 minus -2 dA. So if we wanted to compute this double integral, we could use it using Cartesian coordinates as usual. So if we draw a line in the increasing y direction, we enter at the green curve, y equals x squared. We exit at the orange curve, which is square root x. Out of all the possible y, like vertical lines we can draw, what is the smallest x value? It's 0, and the largest is 1. So we have 7 dy dx. And you can keep computing the integral, and you get 7/3, which is our same answer, and that was way much shorter. Any questions on that? Okay, let's do another example. So it says, find the flux of this vector field out of each side of a dodecagon, meaning a 12-sided polygon. Oh, with, you see here, it says positive flux in the direction of the outward unit normal. So now we know we can compute flux normally. So there's two ways you can do this. First way, which is using last week's material, because this is a dodecagon, you would have to compute the integral over each side of our shape. That would take a long time. We have 12 integrals. Or we see that it's a simply connected curve, and we start and end at the same point. So we can use Green's theorem, which assumes outward unit normals. So our function, the m term is going to be y, the n term is -x, using my vector field. And let's use Green's theorem to find this integral. So here, the integral, or the partial of n with respect to y, that's going to be 1. Partial of n with respect to x is -1. So actually, we end up getting this double integral of 1 minus 1 minus 1 dA, which is going to be integral of 0. If your integrand is 0, well, there's no way you can get any area. So it has to be 0. Yes.
Wait, is it like partial m with respect to x or with respect to y?
Oh, this is to. Oh, this is the flex definite like form. So that's like the second formula. Partial m over x plus partial n over y is for flux. And like my point in the purple thing was that if you forget what this flux definition is, you can always derive it from the green box theorem. So the green box, this circulation version is the one you definitely want to know for sure.
So if you go back, right?
Mhm.
Then you take m with respect to y.
Oh. Right, wait, m over x n over y. Okay, so whoops. So then with respect to x, you still get 0, and over here you get 0 also. So you still get 0. Yes.
For this question, you dx dy into dA, but the last question you kept dx dy as dx dy. Can you just explain why you changed one and not the other?
Because so this one, if we had more stuff to compute, then I would have changed it to dx dy, so that we know the order of integration. But because we already get 0, like we don't need to know if we're doing dx dy or dy dx, so I just left that as dA.
And then Professor Bryce like sometimes would like plug the actual like area formula, for example, like the circle into like what dA is.
Mhm.
When do we know like we have to do that versus when we have to like actually integrate dy dx?
So if you get this integral and say like this expression in here turns out to be a number, like 7 dA, then by integration rules, we can bring out this 7, so we get double integral of 1 dA. And we learned like a few weeks ago that the double integral of 1 dA by definition is area of your shape, of whatever shape. So that's why he does 7 times like area of whatever circle. Just like we know how the triple integral of 1 dB, that's the volume of your shape, and etc. So we know like area and volume. Okay. And actually from that, from Green's theorem, we can actually get what the area of some shape is. So from Green's theorem, there's like a corollary that the area of some region we can calculate as these 3 equivalent definitions. And here I prove why they are, but so let me, so that's just like a side note. Okay, why don't we take a 5-minute break now before I give some more intuition. So come back at like 2:37. Okay, so more intuition about Green's theorem. Okay, so if you have some curve that looks like this in the first quadrant, this integral, like if you took it, it would end up being 0. So the reason why is because Green's theorem is kind of doing like, it's kind of looking at your change in theta. So imagine I draw our starting point and theta is like pi over 4 or something. As I travel along this curve, say when I get to this point, my theta is smaller. And so we see this is a graph of like theta over time. Theta was pi over 4, and then it got smaller, and then you keep on going up, and then eventually you get back to the same theta. So there was no change in theta, so the integral over this path would be 0. However, case 2 is where, and this was mentioned in the videos, he has this other curve. The only difference now is that it passes, like the origin is in this region. So you can't take this integral because at 0, it would end up being discontinuous. And so the reason in the video, like, so what he does in the video in order to get rid of that discontinuity is he cuts out a circle. So I cut out an orange circle here. So that way I can remove the problem, removing the origin.
That's a whole, right? And you can't use it in Green's theorem, right? A whole.
It is a whole, but we're gonna do something else with it. So you'll see that, so we do get rid of this whole. And this is, let me call this C hat first. So we see that our outer curve is going counterclockwise, but I drew my orange curve. Did I draw it clockwise? This is because our region right now is this purple region. And imagine you're walking on this outer curve. Then if you go counterclockwise, like imagine your left arm, long arm, is going to be in our shaded region. When you're walking on the orange curve, we want to go clockwise because we always want our left hand to stay in the region. So imagine you're walking like clockwise, then our right arm is going to be inside our hole. Our left arm is going to be in the area. So our orange curve has to go clockwise, not counterclockwise. So now we have this large thing with something cut out. We're going to say that the boundary of our shaded region, we're going to take care of that like hole by saying that the boundary is going to be the union of the black curve and the orange curve. So I'm going to take the union, that's the boundary of our shaded region. And so now, since we have some boundary, we can use Green's theorem over this union boundary. And so what does Green's theorem say? Well, we can break this up into two integrals. Integral over C plus integral over the orange clockwise curve. Now, if I don't want to deal with this negative C, I can bring out the negative. So it becomes minus the integral of C hat dot dr equals 0. And this tells us that no matter what, the integral over our outer curve, integral of this over the orange smaller. And so you might ask, what if that orange circle that I cut out, what if it's like a different circle, like it's bigger or smaller or whatever? Well, I'm going to say that it doesn't matter because no matter what you choose for C, your C hat, well, if we change C hat, we get some other number here, but we set that equal to the integral over C. So our integral over C will also be changed. And so no matter what, you have thing equal something else, but you're subtracting it. So you're always going to get 0 no matter what. Any changes you make to C hat will end up canceling out at the end.
So I have two questions.
Mhm.
First one, so does it hold? It doesn't hold that then we can. It has to be in a simple closed planar curve of hole. Right? I don't really get it. Why did you make a hole in the diagram? And the second question is, like, what's the representation of like the of the integral with the bounds of C and everything?
So we're trying to find what is the integral of this shape. That's the first question at the top. But we can't do that because our function is discontinuous at the origin. So we don't want this problem. So we're going to cut out the circle. Even though we cut out a circle, now there's a hole, we define our boundary as the union of the black one and the one. That's fine because that's still like this is just something else we're doing so that we can try to find this integral, like the integral of the thing. So like, yes, if you're given this second picture just as it is, like you can't use Green's theorem. But because our actual question is to find this integral, we're trying to do other strategies, and that other strategy is just cutting a hole. So the point of this is just to show you like what this top integral ends up being, which is 0. Yes.
When you tell the direction from the drawing that is discontinuous, it was discontinuous in the video because of like X with Y with.
So yeah, you should be given the function and see if like the denominator can't equal 0 or something.
You can't tell from a shape, like from that, like.
No. Yeah. So okay. Yeah. So maybe I should say like function. This. at 0, 0.
And then also just with like the direction of like
Mhm.
so the outer boundary is always going to be counterclockwise, and then any holes inside is going to be
The other way.
it's going to be the other way.
If you're, it just has to be like opposite. So if you're, oh wait, yeah, the outer, if you're gonna cut a hole, the outer one has to be counterclockwise, and then inner one would be clockwise. Because if your outer curve was clockwise, then you can't, then there's no way to like cut a hole. Because if you're imagine you're walking on this path, your left hand is on the outside. So your region would be like this outer region. And so you would need some other curve outside it to be clockwise, which is exactly just this first picture.
So wherever your like hypothetical left hand is,
Mhm.
direction will be, that's like the area.
The region, yeah. Yes.
Can you go over the answer that we got from the previous?
Yes. So I end up getting that the integral of my big region with that discontinuous hole in it equals the integral of my orange circle. So if I can find the integral of the orange circle over the orange circle, then it will equal the integral of this entire thing. And I guess you might say like the origin is also in this orange circle. But we don't care about that because we just found that equals this. So no matter what, even we compute what I highlighted in green, overall you still get like some x minus the same number. So it has to be 0. It doesn't matter that I can't compute this green thing. Okay, any other questions before I move to differential forms? Yeah. I'm making a hole because my function, say it's like x over x squared plus y squared, and whatever second term. When you do the Green's theorem, or even if you do the parameterization method, we plug in our parameterization into this function. But at the point 0, 0, our denominator does not exist because you can't have something divided by 0. So at this point, how can you take the integral over this region if it's discontinuous at 0? You can't. It has to be like your function has to be defined in order for you to take an integral. So we need to get rid of this discontinuous problem, cutting out a circle. Okay, let's do some discontinuous forms. Okay, so here we have some discontinuous form. Sorry, not differential forms. So you have the 0 form field, which is just f, like the scalar itself. 1 form field is where f is given as f2, f3. Then your 1 form field is defined as f1 dx plus f2 dx plus f3 dz. Then with some vector field, there also associates a flex 2 form field. And that's this definition. So now we have this wedge product. And I'll talk about the wedge in a few minutes. So these are our formulas. Given some vector field, you can always use these definitions to find your 1 form and your 2 form, or a 3 form. Oh, and a 3 form is defined as f dx. 3 form is f dy. And you might say, how do you remember like what this 2 form field is? Like this definition? One way you can remember it is that I drew this diagram. So I have the z components together, the x components together, and the y components together. And what you do is, so say the first term, I have an f1. I start at f1, which is my fx, and then I follow these arrows. So I have fx, I go to the middle circle, and then I follow the arrows to get dy, dz. So we see our first term is f1, dy wedge dz. How could I find this second term? I start at fy, I move to the inner blue circle, and I get dz, dx. So it's f2 dz wedge dx. And you can do the same for f3. So this is a nice way of remembering like what goes with what.
Sorry, how do you go inside the circle?
So you start on the outer circle with whatever f function you have. So like f1 is fx. Then I go to the inner circle. I've already used this x term. So I go to the next one, which is dy dz. Yep.
Wait, so this is not just like a root two form in general, right? This is like the
Flex 2 form.
Yeah, and then so you have just general one form, the flux two form, and general three form on the board.
Yeah, like this is the flex.
What is the symbol? It's not like an of the two.
Oh, this?
Yeah.
Oh, it's a fee, like this. Or sometimes better. Or sometimes not like that. I don't know. Like some people do, it's just this circle.
So the three form field, how would you express it?
It's some scalar field, and then this wedge product. I don't think there's a.
There's no F1, F2.
So this is using. So F1, F2, F3 helps you find the one form and two form fields, but the three form field is your actual like lowercase f. Same as how your zero form is just some scalar function f. So these two are not using some vector field. This is just using a normal scalar field, like f is like 2x plus 3. So if you're given this function, then your three form would be 2x plus 3z ln 4x.
So it would only apply to the three C terms, right? The what? The,
No, it's like
oh, okay.
so let's do an example of finding it, right? So if we're given some vector field here, negative x squared j, notice I put the j here, plus vi plus yk. What should my associated one form field be? So I'm given a vector field function. I'm given this. How do I find my one form? Can someone tell me what I should write for alpha?
CDX.
Oh, z dx.
And then the minus x squared y.
Mhm.
Y.
Yes, exactly. Yes.
Wait, I'm confused. So the zero form is a scalar function order. What does that have to do with the f1, f2, f3?
It's separate, so that's why I like drew a line.
Wait, so like I'm confused. Like so
So you have a scalar function f,
yeah,
which is a zero form.
okay,
If you took the derivative of f,
yeah,
that gives you the one form.
okay.
If you took the derivative of the one form, it gives you the two form.
The flux two forms.
Plus two form.
Okay,
If you took the derivative of that, you get the three form.
okay. And basically, you take the derivative, and that you can like take out the f1, f2, f3, and that will give you that thing up there.
Yeah.
Or no, for the one form, you take the derivative, you get f1, f2, f3, right? That would
Yes,
yes, okay.
yes. Okay, so this question here, the trick was that I wrote like j first. So be careful that you don't just say alpha is negative x squared dx plus z dy plus j dz. You have to make sure you're matching the I and the first component, like the I with the dx, the j with the dy, and the k with the dz. Okay, if it says to find the flux two form, well, now we already know what f1, f2, and f3 are. We just have extra wedges now. So it would be z dy wedge dz minus x squared dz wedge dx plus y dx dy. Because this is our first component, which we saw as z. This is our second one, then this is our third one. Any questions on that? Okay, note that for the flux 2 form, I wrote this purple thing. But note that there's lots of different ways to write this phi sub f, this flux 2 form, because of our wedge properties. So like our wedge properties, we could see like, we could write this entire thing. We could say that phi is also negative z dc dy, and then the rest. And there's lots of, you could try all different combinations because we have the property that if you want to flip your wedges, a negative sign comes out. Okay, so let's do, okay, let me talk about this. So as I just mentioned, oh wait, actually, no, this is a different thing. So this is talking about, for any vector field, the associated one form field. So it says one form, it can eat one vector u, and it returns a scalar. For any two form field, flux 2 form field, so we have 2, you can eat 2 vectors, and it would give you a scalar. How do you compute that? Like, how do you compute a flux 2 form eating a vector? Well, we can write it as this flux 2 form evaluated at whatever point they give you, dotted with the cross product of our 2 vectors. And we need the cross product of our 2 vectors so that we can get a number and therefore do the dot product. Or another way we can do this from like the very first week of class is that we can rewrite it as the determinant of like your flux 2 form evaluated at your point as your first column, then u, then v. This is equivalent to writing it as like, if you wanted to write it as columns, or sorry, rows instead, you could also write it like as rows. And that's because the determinant of A equals the determinant of A transpose. So it doesn't matter if you write it as columns or as rows. Yep.
I have 2 questions. The first one is, how would you do it as that cross? Like, if you found a cross product of u, how would you then, like if you didn't use the determinant method, if you found a cross product of u, how would you apply that to the 2 form?
So cross product. Okay, actually, wait. Cross product gives you a vector. Sorry, yeah, a vector. So you would have this 2 form, like each term evaluated. So like x, let me call it xyz is our flux 2 form with numbers in them. Dot with your cross product also gives you some number a, b, c. And so the dot product is xa plus yb plus cz.
And that's equivalent to taking that
Mhm.
determinant. Okay, and then my next question, well, also, so they did that like in the way like Bruno showed us was he like kind of he like lined it up and it was like the first one is dx, the second one is dy, the third one is dz. So if you want to find, dx wedge dy, you would take the determinant of the first square, if you know what I'm saying.
Yes. So if you have like, I guess I'll just do it on here. So like if you had a flux 2 form that was like, I don't know, x, y, z, like, okay, wait, there was a practice problem question. No, prep quiz question. Number 5. Wait, no, 6. Oh, 4. 4. So you could do it as, we see they're asking you for dx minus z dy wedge dx. So I can plug in my point 2, 1, 3 into this. So I get 3 times 2 or 6 minus 3. So I get 3 here. Then dy wedge dz is going to be, if I wrote our two vectors as some matrix A, 0, 2, negative 1, 3, 0, 1. Let me write it in purple. Then the dy wedge dz is telling you the projected area to the yz plane. So the yz plane would be this, the y numbers and the z numbers, which is this or highlighted square. And so you take the determinant of that, which gives you 2. Then it says this negative, this y squared plus z squared. So I evaluate at my point, which gives me minus 10. And then dx wedge dy, I want to line up. Oh, wait a second. Y, z, okay. I get my x row and my y row. And I take the determinant of that, which is 6, negative 6.
Wait, is it c squared 1?
Z squared is,
Oh, sorry.
so 1 squared plus 3 squared is 10. And then I have negative sign out here. So minus this. Wait. 1 squared plus 3 squared is 10. Yes. So here I have a minus 10 times negative 6 or plus 60. And this is 6. 3 times 2 is 6. Minus 10 times negative 6 or minus negative 60, which is 6 plus 60 or 66. Yeah. Yes.
Wait, so. Oh yeah, so if they were asking us one with like dx wedge dz,
Z.
how would we do that?
Then you do the first row and the last row.
And what can you multiply that by?
So that then this determinant is 0, 1, 3, negative 1. So 0 minus negative 3 or 3. So you would get whatever expression times 3. Like if you had some blank expression times dx wedge dz, that would equal whatever this expression is times 3.
Or would it be dz wedge dx?
Sorry, yeah, d
It's the way to.
dz, yes, dz wedge dx.
Wait, why would it be that?
I wait, dz, I think it would then flip it though.
Wait, why would it, wouldn't it not flip? Because wouldn't it flip it if it's dx wedge dz? Because the way the two form is written is dz wedge dx is f2. So if we have f2 and we're using this,
Let me see. So in the videos, it says that dxi wedge dxj of some vectors is going to be ui vi uj vj. So if we wanted to do dz wedge dx, then you should have the first two components of your, so u of I, so u of the z component, which is negative 1, then u of the x component, which is 0. Then our v vector, the z component is 3. And our v vector, the j component, or the x the x component is 3. I switched it. 1 and 3. 1 and 3. So just follow the formula.
okay, but if we did the full like 3x3 determinant thing like we have up there,
Yep.
how does that make sense? Because
It's still, you still get
all-
66.
Well, yeah, but if you have MNP or whatever.
So, okay, so look, so you have right now for your my first thing, I have 3 times 2. 3, which is here, and 2 ends up being this dy.
Yeah, I get that. I'm talking about the dz part because f2 is n. So would you cross that way and we'll just take 0, 3 -1 is 1, and multiply it by n, which is f2. But that you're not flipping. So I don't understand if we do it with the 2 by 2 and flip it, or if we just, you know what I'm saying?
Let me see. 0, -3, 6, or 2 times -3. Minus.
I mean, it doesn't apply in this question because there's no dx, but I was just asking, should they be the same?
It looks like
Or what are they?
let's see, you get 2 times, right, 2 times 3 is -6. Yeah, it might be off by like a negative sign somewhere. So I'm not. Wait a second. How did we oh, sorry, this was a 0.
Yeah, so it
Yeah,
doesn't apply to this example, but in another example, with those two get the same value.
Right, it should, I believe it should give the same value by the formulas. I'm not sure why it's working. So let me get back to you on that because we're running out of time. And let me continue recitation. So just ask on Piazza if I forget. Okay, so here I have an example, but we just did an example, so I'm going to skip it. So let me give you intuition about what is this wedge thing we're doing. So given 2 vectors like u and v in 3 dimensions, we know that the cross product, the magnitude of the cross product, gives us the area of a parallelogram. This is from like week 1 definition. Then a question is, what is the sign projection of this area onto the xy plane? So if you think about the matrix that we wrote right here, then we just want the projection onto the xy plane. So if I take the x coordinates and the y coordinates, I get this 2 by 2 matrix. So the sign projection onto the xy plane is going to be this determinant, u1, v1, u2, v2. And that definition is written as dx wedge dy, where so this is a 2 form eating 2 vectors. So the 2 form eating 2 vectors, or you can do this determinant. And so what is it like pictorially, I guess? If you have these 2 vectors, like this u vector and this green vector, the v vector, we project it onto the xy plane to get this purple shaded region. And that's going to be our projected area onto the xy plane. And what do I mean by signed projected area? Sign just means that we're doing it on top of the x-axis or either on or above the x-axis. So it's going to be a positive area. If I like projected it below the x-axis or somewhere, then it'd be a negative area. So we're just considering the positive area for now. And so in general, d some variable, wedge d some variable, eating 2 vectors are going to give you the projected area onto this variable plane. And so that's like one of the practice problems. And then we have the wedge product properties. So here's associative, distributive. The most ones we're going to use are this anti-symmetric property, where if you want to flip the 2 vectors or 2 numbers, you get a negative sign. And if you're wedging 2 of the same things, you get 0. Okay, so let's do an example here. So I have, what is the area of the projection parallelogram spanned by these 2 vectors on the YZ plane? Okay, so I said that the formula that we do is going to be dy dz because we want the YZ plane. And this two form is eating these two vectors, u and v. And so for my determinant, I take the u and v components. So that's going to be 1, 2, 2, 3, or 3 minus 4, which is -1. But we know that area can't be negative. So that's why we said like the sign projection, signed projection, or we take the absolute value. So the projected area is going to be 1. Any questions on this?
It's the magnitude always.
Absolute value.
Oh, sorry, I think magnitude. But always, right?
Yeah.
But I mean, it's not real area, right? It's projected.
Yeah. Projected area. So if you have like if you have the absolute value of some number, like with the bar, that always means that it's absolute value. If you had a vector in here, that tells you that it's magnitude. Okay, question. What is dy wedge dx wedge dy? Yes, it's 0. So equals 0. And that's because either you could use wedge properties and we can flip these two and we see that we get dy wedge dy, which has to be 0. Or you can also see by looking at the determinant. So if you had some 3 vectors, u, v, and w, this tells us to take the y component first. Y. Then the x tells us we want to take the x component next. And then finally, we take the y component again. Well, we know the row reduction properties that we see these two rows are exactly the same. So if we wanted to like row reduce, we'd end up getting a whole row of zeros. And so this determinant is 0. And it makes sense because you think about, we have these two, we have these two vectors. If we have like 2 vectors u and v, and we let the 2 form eat the 2 vectors, well, the volume spanned by 2 vectors is 0 because 2 vectors is only on one plane. There's no volume. So it makes sense that this wedge product is 0. Okay, any questions on that? Okay, then we have differentiation, which I said like, it just means that if you go from, take the derivative of a 1 form, you get a 2 form, and you keep going down the list. And so let me quickly do an example here. If you're given some 2 form that looks like this, and we wanted to take the derivative, what do? We first split it up. So I want the derivative of the orange thing, plus the derivative of the green thing, plus the derivative of the purple thing. Let's focus on the orange. So if I want to take this wedge product out, this differentials, the dx dy, another wedge comes out. So I'm left with just the derivative of our first term, wedge dx wedge dy. Now I take the derivative of x squared. The derivative of x squared is 2x dx. And this wedge continues, wedge dx wedge dy. Turns out that dx wedge dx is 0. So this first term ended up being 0. But you can keep continuing it with the green and the purple, and we get 2y this. Any questions on that? Okay, or we can notice that, so we see that this is a 2 form. There are some special properties where if you have any scalar function f, so scalar function f, which is the 0 form, then the derivative, the derivative of the 0 form is going to be associated with the gradient. The derivative of the 1 form field is going to be associated with the curl, which is this definition. And the derivative of the 2 form field is going to be associated with the divergence. So instead of doing all of this differentiation, which would take a long time, we could realize that it was a 2 form field. So we could realize that it was just a 2 form field. And let me, I have it written out instead. We could have just written that it's a 2 form field. And we said that it's associated with the divergence of f. And so I can just directly calculate the divergence. which I get 2y, and then I add in the wedges. So that's an easier way to compute it. See how we just went to 2y and got the answer. Any questions about that? Okay, last thing is that I have this nice table here that might be good to look at. And I did do practice problem 8 here. Okay, but now recitation is over.